All right, so last time we started talking about linear interpolation. Last time we did we used one independent variable. So in that case, you have a function like that, and you have your points x1 and x2. And you're trying to approximate it at some value x, and you approximate it by that red dot. So you're just, mathematically, you're putting a line in between those two boundary points, and you're following that line to approximate your value at the x value you want. So now we're going to two independent variables. So linear interpolation for two independent variables. And let's think for a second, relating this to properties of materials and thinking about the tables. What are the cases where we're going to use linear interpolation with one independent variable? So remember I said that in some cases, all you need is one property to specify all the other properties of a material, and in some cases you need two. Remember what that is?
On the vapor dome, what's it?
Yes.
What's the line?
The saturation, at the saturation states, all you need is one property to specify all the other ones. So for one independent variable, this will always work at saturation states, whether it's a saturated vapor or a saturated liquid. Two independent variables we're going to use for a compressed liquid. Or a superheated vapor that is away from the vapor dome. There are cases, by the way, and sometimes I'll cook these up in problems because it saves some time on tests or whatever, but there are cases where, like, I'll ask you for something that happens will be at a pressure of 5 megapascals and a temperature of 67 degrees. And maybe in the table, 5 megapascals just happens to fall right on the pressures that they give, you know? And so then even though it's depending on two variables, you'll only have to do one interpolation. But in general, you need two independent variables when you're not at saturation. Okay, so what does this look like? Like mathematically, if you're looking from above, you have an x1, an x2, a y1, a y2, and the point you're trying to calculate is like that at x, y. Okay. And so this is two independent variables. That's why this doesn't look like a function. The equivalent of the function is a surface over the top of this. Okay, so we're like hanging on the surface like a roof ceiling. I mean, looking down at the floor. So from the side, or sort of from the side, you'd have a surface like that. Underneath, you would have your values like this. Ooh, this is, I can already tell this is coming out so good. Sometimes drawings go wrong right from the start. Okay, so this is x1, x2, y1, y2. And the approximation we're trying to come up with is, say, here. Well, let me put it in the same spot, I guess, as before. So it would be like over here. So that's the x. That's the y. And it would be like that. Any questions about what's going on here? All right, so how do you do this? So to approximate the function f of x, y, you're going to start with f of, okay, you're going to start with 4 of these values. Let me just write them out in a grid first like this. Okay, so over here, this is the function x1, this is the function x1, y1, of x1, y1. This is x1, y2. This is x2, y1. And this is x2, y2. Okay, so I position them in the location that corresponds to like this picture here. Okay. And now you're going to do 3 applications of that linear interpolation equation. So the first one, we're going to calculate f of x, y1. And the way we're going to do that is, this is an approximation, but we're going to imagine that y1 is fixed. Okay, for this application, we'll just leave y1 fixed. We know what that value is. And we'll do the interpolation on x. So this is going to be f of x1, y1 plus f of x2, y1 minus f of x1, y1. Notice the y1s are just hanging in there, like not changing at all. And then we're dividing by x2 minus x1. And then multiplying it by x minus x1. Now we'll do the same thing, but using y2 as if it's constant. So f of x y2 is f of x1 y2 plus f of x2 y2 minus f of x1 y2 divided by x2 minus x1. And this slope is multiplied by x minus x1. And now that we've interpolated, so let's think about what we've calculated here. So first, we calculate the function at the smaller y value at our desired x value. So like here, you can think of it as we're calculating, so the two first steps are the green point here. The second step, we're doing it at our desired x, but at y2, so that's the blue point here. And then the last step is to interpolate along this line between the blue and the green values. So f of x, y, finally, our approximation, is f of x y1 plus f of x y2 minus f of x y1 divided by y2 minus y1 times y minus y1. Okay. Could you go in the other order? Could you calculate f of x1 at our desired y, f of x2 and our desired y, and then interpolate on x? Yeah, that's fine. You don't get the exact same answer, but it's close, and these are both approximations. Okay. Well, I should say it's close for pretty calm, well-behaved functions, and thermodynamic functions tend to be that. Okay, you don't get like wild oscillations or anything. So remember that, what are we talking about here for, like, what are our independent variables? This is all kind of abstract still, but so what we're trying to do here is, if we have a superheated vapor, say, so it's not at saturation, and we're trying to calculate the specific internal energy at a given temperature and pressure, okay, then our x values are going to be, say, temperature, and our y values are going to be pressure. And we're going to look up the corresponding specific internal energy at each of these four, combinations of temperature and pressure, and then do this interpolation to estimate the specific internal energy at our desired values of temperature and pressure. Okay. All right, well, let's see this work for just a function, and then let's see it work for properties. So let's say we have this function, this simple function x squared y squared. And let's say that what we want is to approximate this function at 2, 2. And to do that, we're going to use these values f at, let's say, 1.8. Let me put it in the right order. So f of 2.2, 1.8, f at 1.8, 1.8, and then f at, what am I doing? 1.8, 1.8, 2.2, sorry about your notes. Okay, then f at 2.2, 2.2, and then f at 2.2, 1.8. So those are our 4 values, and I'll calculate those real quick. These would be like the things that you'd look up in the table. So 1.8 times 2.2 squared. So this is 15.68, and that's the same thing as this. And then this is 10.50. And this is 23.43. Okay, well, the true value is 16 for this function. So we're going to see how close we get to 16 with this approach. So the first step, I'm going to calculate f at 2, and then with a y value of 1.8. Okay, so I'm going to go f at 1.8, 1.8. Plus f at 2.2, 1.8. Minus f at 1.8, 1.8. Divided by 2.2 minus 1.8. Multiplied by 2 minus 1.8. Anybody have any questions about this yet? Okay, so what do we got? So for this, I get 13.09. Now for the second step, we're going to go f at an x value of 2, and a y value of 2.2. So we'll go f of 1.8, 2.2, so 15.68, plus f of 2.2, 2.2, minus f of 1.8, 2.2, divided again by 2.2 minus 1.8, multiplied by 2 minus 1.8. And I get 19.56. And then last, we'll use these two values that we just calculated to approximate, and I'm going to change these to approximate equal. So f at 2, 2 is equal to f at 2, 1.8 plus f at 2, 2.2 minus that original one again, divided by y2 minus y1, times y minus y1, and we get a value of 16.32. Okay. So this is our final approximation of this function. And the true value, the real value, is 16. So you see how that sort of works.
If you take the average of the points that were given at the top,
Yeah.
the values of those points, you get almost the exact same.
Yeah, that is because that's because I chose the exact center of that rectangle, you know. So that doesn't work if you're off of the center. But I guess if you're exactly at the center like that, then that'll work. Okay, let's do a 1D problem from the table, and then we'll do a 2D problem from the table. Okay, so let's look at the table for refrigerant 134A. And let's figure out what the specific internal energy for a saturated liquid at negative 9 degrees Celsius. And I'll put these back up. Okay, so approximate the specific internal energy of refrigerant 134A at -9 degrees Celsius. Okay, so the values you're going to use are the saturated liquid internal, specific internal energy at -12 and -8. See if you can work through that. Okay, so from the table, you can see that the specific internal energy of refrigerant 134A at a temperature of -8 degrees Celsius is 39.38 kilojoules per kilogram. And then at -12, it's 34.25 kilojoules per kilogram. So for the approximation, we're trying to approximate this at a value of -9. That's going to be the one at x1, so 34.25, plus 39.38 minus 34.25, divided by -8 minus -12, times -9 minus -12. And you get a value. Does anyone have that? Anyone get that? I'll do it. Oh, times 3. Okay, so 38.10. Any questions about that? Yeah.
I switched them.
Yeah,
I got the
same thing, yeah.
Okay.
Yes, it is okay, yep. You're just going back along the line instead of forward along the line. Actually, that's what I did at first too, and then as I was doing it here, I'm like, oh, -12 is less than -8, but it works fine. All right. So now let's do one more thing for this, the saturated cases, and that is called quality of a saturated mix. Okay? The quality and it's just called lowercase x. When you see this lowercase x, that's what we're talking about if you have saturated material. And the definition of it is the mass of a vapor divided by the mass, well, I'll just write it as the total mass. Okay, so the way this works is if the mixture is 100% vapor, X is equal to 1. If the mix is 100% liquid, X is 0. And in between those two, you get values in between 0 and 1. Okay. Why is it defined this way? Does it make sense to, so, and where does like the word quality come from? Well, remember that if you think about latent heat, a vapor, a saturated vapor has a lot of energy stored in it, a lot of internal energy that a saturated liquid at that same temperature and pressure doesn't have, okay? And so in a sense, this quality is telling you at that temperature and pressure how much of this stored energy you have, okay? So think of quality that way, like think of something that has a lot of quality is something that has a lot of this invisible stored energy that we can access, okay? If you think about it that way, it sort of makes sense. If you think of it as an engineer who wants to use that energy, we want something that has like a lot of stored energy that we can get at, you know? And the benefit of this is that for any property Q, the total value of the property is equal to the quality times the property for the vapor plus, notice that 1 minus X is like the mass fraction that's a liquid times Q for the saturated liquid at those values. So now, you know, you can replace this variable Q with whatever property you're looking for. This works for specific internal energy. It works for pressure, temperature, specific entropy, specific enthalpy, and on and on. Any property that you can look up in the table, once you know the quality of your saturated mix, you can use this equation to calculate the specific property of the entire mixture. Okay. Okay, so let's do another example. Might as well keep the same one going. So now say that, so we're still dealing with refrigerant 134A at negative 9 degrees Celsius. From the example above, we know that for the liquid, a saturated liquid, U at a value of negative 9 degrees Celsius was equal to 38.10. Kilojoules per kilogram. So first now we want to calculate, approximate the specific internal energy at -9 degrees Celsius for a saturated vapor. And then second, if we know that we have a quality of 0.30, calculate the specific internal energy at -9 degrees Celsius for the saturated mixture. Okay, so take a couple minutes and see if you can interpolate again, this time for the saturated vapor from the table. Let's just do A first. I'll give you a little time for that, and then I'll do it, and then we'll finish with that quality calculation. That's pretty good. Okay, so for part A, we're given from the table that at -12 degrees Celsius, we have 220.36 kilojoules per kilogram. And at -8 degrees Celsius, we have 222.60 kilojoules per kilogram. And so the approximate value at -9 is 220.36 plus 222.6 minus 220.36 divided by -8 minus -12 times -9 minus -12. And I get a value of 222.04 kilojoules per kilogram. Okay, well, the last step now is we know the quality is 0.3. We know the specific internal energy for the saturated liquid. We know it now for the saturated vapor. And so we can use the quality equation. So take a couple minutes and do that calculation to get our total specific. Well, the equation says that the total specific internal energy is equal to X times the specific internal energy for the gas plus 1 minus X times the specific internal energy for the liquid. So this is 0.3 times 222.04 plus 0.7 of what we got before, 38.10. And you get a value of (93.28) kilojoules per kilogram. Any questions about that? Okay, what do you have to do if you have to deal with quality in the case where you don't have it at a saturation state? You're at a superheated vapor or a compressed liquid? Trick question. when you're in those states, there's no such thing as quality because there's no mixtures, you know? So remember, quality is only defined at saturation states. Okay, well, we don't have time to do a 2D example. We'll do that next time. I'll give you a couple of problems to work on, and I'm going to assign a couple of 2D problems. But if you have trouble with them, I'd be happy to work through any of them on Friday, so bring any questions you have. Okay?